These are notes for section 5.4, solving special systems of linear equations. When they say special systems, they're referring to the answer or the solution for a linear system. If you watch the previous videos, the solution of a linear system is the point where the two lines cross. Well, sometimes lines don't cross, so they have a special answer. And these special answers we're sort of familiar with from Algebra 1, if we remember no solution and all real numbers. So let me work through a couple of examples, and then you'll see how that relates to our special systems of equations. In order to solve a linear equation, we got to distribute combine like terms, pick on the little guy, get the variable by itself. This is Algebra 1 topic. After we combine like terms, I can subtract 2x from both sides. Those make the x's go away. We're left with 7 equals 3 with no variable. Well, this is not true. Of course, 7 does not equal 3. So what we would say is there is no solution. No solution meaning there is no number that makes the equation true. There's no value of x that will make both sides of the equation the same number. And on the other side of that, we, again, to solve, distribute combine like terms, pick on the little guy, get the variable by itself. So I get rid of the parentheses, I combine these like terms, I move the smaller variable, it doesn't matter which one, they are the same. 3 minus 3 is 0, and I'm left with negative 12 equals negative 12. Well, this, of course, is true. There's no variables left, and we have a true statement. What we then say is all real numbers, meaning every single number you can think of would make the equation true, all of them. So we have two different sides here. We have something where none of the numbers work, and we have something where all of the numbers work. Okay, so how does this apply to what we're talking about with linear systems? Well, if we just think for a moment about two lines in space or two lines on a graph. I have one line crossing another line. This is our normal linear system, and their answer is the point where they cross. Okay, well, if we understand the answer being the point where they cross, we could probably think of no solution, meaning they don't cross. Well, if they don't cross, then that means the lines are parallel. They don't have a point where they cross. There is no point where the two lines cross, no solution. And on the other side of that, again, if we've defined the answer as the point where they cross, well, how could they cross infinitely many times? Well, that would be one line graphed directly on top of another line. They share an infinite number of points together. So you could say this one, this one, this one, this one, all of them, all of the points on the line. We can't say all real numbers because all of real numbers would include this point. Well, that's not on the line. It's not on either one. So this point would not be a solution. So what we have to say is there are infinitely many solutions, and those solutions happen to be on both of the lines. And to shorthand this, we have the no solution symbol if you would like that. You could either write out infinitely many solutions, or I'm fine with an abbreviation, IMS, infinitely many solutions. So let me walk through a couple of examples, and we'll see what this looked like. Again, in order to graph lines, we use slope-intercept form, y equals mx plus b. So m is 2, b is 3. My first point is up here at 3, y-intercept, and then I use the slope, up 2 over 1, or down 2 and left 1. And again, I should graph the entire first line so I can find the point where those two lines cross. So that's my top line. If I pick a different color and graph the bottom line, again, slope is 2, y-intercept is negative 1. So my first point is down here at negative 1. And I use my slope of up 2 over 1, up 2 over 1, up 2 over 1, or down 2 and left 1. Again, I'm trying to find where these two lines cross. Well, they don't. They don't cross, which means there is no solution. They don't share a point where the two lines cross. On number 2, the slope of the line is negative 1. The y-intercept is 2. I graph my first point at positive 2, a y-intercept, and then I use my slope. Down 1, right 1, down 1, right 1, down 1, right 1, or up 1 and left 1. And again, we should graph the entire first line because I don't know where my second line might cross it at. Once I graph the first line, grab a different color here and graph the second line using slope-intercept form. Slope of 1, y-intercept of -4. So my first point is down here at -4. And then I can use the slope, which is up 1, right 1, up 1, right 1, up 1, right 1. Now I can stop here because I found what I'm looking for. I found the point where the two lines cross. This ordered pair is 3, -1. Those lines cross at 3, -1. 3, -1 is the solution. So we have no solution. They don't cross at all. We have one solution. That's what we would typically expect, the point where they cross. Or, in this last example, if you take a look at both equations, they happen to be the exact same. Well, you probably guess what that's going to lead to. A y-intercept of 4, a slope of up 1, right 2, or down 1 and left 2, and I can connect the dots. Now, if I were to do the exact same thing with my second line, but in a different color, you could probably see that these lines are going to be right on top of one another. That's a slope of 1/2 and a y-intercept of 4. Start at 4, up 1, right 2, up 1, right 2, down 1, left 2, down 1, left 2, and obviously these lines are directly on top of each other. They share an infinite number of points, so we can say there are infinitely many solutions. Hopefully that helps. Thanks.